This is the next example from your notes paper. I have a function f of x equals x cubed minus 1, all divided by x squared minus 1. This function has a discontinuity at x equals 1. We could also factor that denominator and find out that there's another discontinuity at x equals negative 1. But the problem here, we're asked to write an extended function that is continuous at x equals 1. So extended function, it's a fancy word for a piecewise function for which you've filled in the hole. So if we think there's a hole at x equals 1, remember that's the only kind of discontinuity we can remove, we're going to write a piece of the piecewise function that just tells us exactly how to fill in that one hole. So remember, if we want this function f of x to be continuous at x equals 1, the function value that we pick for it has to equal the limit of the function, the limit of f of x, as x approaches 1. So here I have a case where it's a limit, like I learned back in 2.1. Hold on. It's a limit that I can simplify by trying factoring with canceling. So you might recall, I hope you recall, it's not a big deal if you don't, that I can factor x cubed minus 1 is the difference of two cubes, so that's x minus 1 times x squared plus x plus 1. I can factor the denominator as x plus 1 times x minus 1. My x plus 1's cancel, and I have a new expression. It's x squared plus x plus 1 over x plus 1. Now can I plug 1 in? I can, and I get 1 plus 1 plus 1 over 2, and I find out that the limit of this function as x approaches 1 is 3/2. Now f of 1 does not equal 3/2, because if you look at this function, I can't plug in 1. But I can write a piecewise function with the hole filled in. So this is my new function f of x down here. It looks exactly like the function I started with for all the rest of the points, for all the rest of the domain. So f of x is x cubed minus 1 all over x squared minus 1, as long as x does not equal 1. At x equals 1, I get to pick the y value. I want to fill in the hole, so I'm going to pick the y value, 3/2. This is an extended function that is continuous at x equals 1. So just notice here, there is another discontinuity at x equals negative 1. Oops. There we go. This is what the function looks like. I'll zoom in here a little bit. This is the function after I've filled in the hole. It would be really hard to see, but if you had zoomed in at x equals 1 before we filled in the hole, there would have been a little hole right at x equals 1, specifically at 1 comma 3/2. Why can't I fix the discontinuity at x equals negative 1? Well, look at the type of discontinuity I have. Here's x equals negative 1. This is an infinite discontinuity. That's an essential discontinuity. It can't be fixed by reassigning one single value. So the discontinuity at x equals 1 is removable. So I have removed the discontinuity by filling in a new function value at x equals 1. The discontinuity at x equals negative 1 is an essential discontinuity. It can't be helped. And just one more idea to finish up this slide set. If two functions are continuous, then if you add them, subtract them, multiply them, divide them, or function them with each other, the result is also continuous. So that can help us prove later that a function is continuous. If I know all polynomial functions are continuous, then if I add two polynomial functions, that result is also continuous. Here, sine of x squared, that's me composing the sine function with the x squared function. Composites of continuous functions are continuous.